motion in 2 dimensions and 3 dimensions. It covers position, displacement, velocity, and acceleration, projectile motion, uniform circular motion, relative motion. You can find them in a timeline. Position, displacement, velocity, and acceleration. One general way of locating a particle-like object is with a position vector r, which is a vector that extends from a reference point, usually the origin of a coordinate system, to the object. In the unit vector notation, r, t, r changes with time t, equal to xi, yj, zk, where I, j, k are the unit vector along x, y, z axis respectively. They are constant. And the coefficient x, y, and z are the scalar components. They are 3 independent coordinates. Has nothing to do with each other. Position r equals xi, yj, zk. The coefficient x, y, and z gives the object's location along the axis and relative to the origin. That is, the object has the rectangular coordinates x, y, z. For example, if r equal to minus 3i plus 2j plus 5k, this means this point is here, and its location is minus 3 to 5. That means the project on x-axis is minus 3. This is positive, this is negative, minus 3. So this projector here to x. A project to y is 2, okay, and project to z is x, y, z. Project z, you get this is 5. If the object has position vector r1 at time t1 and a position vector r2 at the later time t2 equals t1 plus delta t, then its displacement delta r during the time interval delta t is delta r equal r2 minus r1, always the final minus initial by definition. Now look at this one in 2-dimensional, 3-dimensional. This is the red line is the project of the particle. A time t1 is located at this one. This is r1. This is orange, x, y, z. And after delta t, t2 equal to t1 by delta t, it moves from here to here, okay? And their displacement delta r is r2 minus r1, okay? Is this one, okay, is this one, okay, and this one. Now, we do it, r2 is x2i plus y2j plus z2k. r1 is x1i and y plus yj plus zk. And you can write it x2 minus x1i, y2 minus y1j, z2 minus z1j. This is a vector. Is vector. Okay. So r2 minus r1 is this one. Delta r. Velocity, 2-dimension case. Okay. Now, the particle moves this way. Its velocity always tangent to this curve. Okay, and we can divide this v as a vx along x direction and vy along y direction. So we can say that v can have 2 components. One is vx, one is vy. Or we can say otherwise. These 2 vectors, the sun is v. Okay. By definition, V equal to delta R of delta T limited T equal to 0. Okay, this is delta R delta T is the average velocity. If we take delta T smaller approach to 0, you take the limit, and this is the definition in calculus dr dt. Okay, dr dt. This is a 2-dimension. Okay. Now we see V equal to dr dt. This is R can be write xi plus yj plus zk. X, y, z are changed with time t. So we put this one in sign. Yeah. Since ijk is a constant, so we can rewrite this one as dx dt I plus dy dt j dz dt k. And at the same time, V is a vector. So it has 3 components, Vxi plus Vyj plus Vzk. We compare these two in front of I, in front of j, plus k, and we find Vx equal to dx dt, Vy equal to dy dt, Vz equal to Vz. This is exactly similar to the one-dimensional situation. V equal to dx dt. Okay. And the speed is the magnitude and the velocity equal to V equal to square root Vx squared plus Vy squared plus Vz squared square root. Sample. A man on a terrace is pulling a block of mass M on the ground. Throw a small pulley as shown in the figure. Suppose h is the height of the terrace. S is the distance of the block to the bottom of the terrace. V0 is the velocity of the man. What is the velocity of the block? Very simple question. Vm, now, V0 is dr dt. The change rate is its velocity, right? For example, it moves 1 meter, so the velocity is 1, and then that means in 1 second it moves 1 meter. So this dr is shorter than 1 meter. So dr dt equal to V0. Okay. Now, this Vm is V0. This is angle theta, cosine theta, or someone say, I like CC. V0 is Vm cosine theta. Just the opposite. Which one is right? Okay, we just guess. We should give them some scientific foundation. Let me see. V0 equal to dr dt. I have explained it before, right? Yeah, because in V velocity is the speed distance per unit time. If this go 1 meter, this is short 1 meter. So dr dt equal to V0. And the block mode Vm. Vm equal to ds dt. Right? Yeah, correct. ds dt. And then we see we want to find that relationship. Actually, we want to find the relationship R and S. You see this one? S in this rectangular, S square equal to R square minus H square. So S equal to square root R square minus H square. Now, we want to find some, we find a V. V is ds dt. We want to relate it to R, V0. What we do, this is according to calculus, ds dt equal to ds dr and dr dt. Okay, remember that? We can cancel out this one because ds dt. And dr dt is V0. Now, let's see this one. What is the ds dt? Now, we do the derivative of S relative to L. So this is equal to half. This has become half minus 1 because minus half 1 and the 2L. This is a very simple one. We get L over S. This is L, this is S. Okay. This is larger than 1. This is L, this is S. This is larger than 1. So we want to see Vm equal to L of S V0, or V0 equal to Vm S of L. S of L is this cosine theta. Okay, so our answer is V0 equal to Vm cosine theta. This conclusion is based on a solid scientific calculation, definition. Average and instantaneous accelerations. We know A average is delta V delta t. In time interval delta t, the velocity change delta v. And instantaneous acceleration equal to the average acceleration takes the delta t approaches 0. And this one in calculus is definition, okay, dv d theta, dt, dv dt. Okay. And this acceleration is a vector. It will have component ax and ay. In this case, look at ax is along x direction positive, ay is along the negative y direction, and this is a. Acceleration a equals dv dt. Since v is dr dt, so a is second derivative of r respect to time t. Rewrite it, okay? This is dv dt, this is the v, okay? This is the second derivative of r respect to time t, okay? And we know ijk is a constant, ijk. So this one actually is dv x dt I plus dvy dt j plus dvz dt. And here is second derivative of x with respect to time t I plus second derivative of y with respect to time t, and so on. And A itself is a vector. It has 3 components, axi plus ayj plus azk. Now, we compare the coefficient in front of I, j, and k. We get ax equal to dvx dt. Second derivative of x with respect to time t. And then we switch x, replace x with y and z. We get ay equal to d dt vy, or second derivative of y with respect to time t. So z, az equal to d dt d vz dt, or second derivative of z with respect to time t, similar to the one-dimensional situation. Example: the position vector of a particle is initially r1 minus 3i plus 2j plus 5k. Now, this is we have met before, okay? And then later is r2, 9i plus 2j plus k. What is the displacement from r1 to r2? By definition, displacement dr equal to r2 minus i1, final minus initial. Okay, we put this one inside. Okay, we put one inside, and we get the answer very easily. Okay, this is x2 9, x1 is minus 3, minus 3. Y2 is 2, y1 is 2, z2 is 8, z1. So we get this answer very simple. Okay. Sample: a rabbit runs across a parking lot on which a set of coordinates axis has, strangely enough, been drawn. Okay. The coordinates of the rabbit's position as a function of time t are given by x equal to minus 0.31 t squared plus 7.2 t plus 28. Y is 0.22 t squared minus 9.1 t plus 30, all a function of time t, with t in seconds and xy in meters. Question A. At t 15 seconds, what is the rabbit's position vector r in unit vector notation and as a magnitude and an angle? This is a very simple question, straightforward. We know the equation, and we put the t equal to 15 seconds, and we get an answer. Okay, get this up. And it's r equal to xt and t. Okay, when it's 15, 16, we find this one equal to 66, and y equal to minus 57. So this is r in, okay. And the magnitude of r, now look at this one. This location at t15, okay. R is 66x here. Y is minus 57. This is y, this is x, y is this one. So this is location r, okay. The magnitude of this r equal to this square plus this square, okay. So the r is rx squared plus y squared, square root. We put this number inside, we get 87 meters. And the theta, remember, tan in the theta, this one, is always y component over x component. So this is y over x, okay. We put them inside, according to the situation, we can get theta, okay. This can have a two answer. We pick up minus 41 in this situation because of the location. Question B, graph the rabbit's path for t equal to 0 to t equal to 25 seconds. Now, we give it the position with time t. We put t equal to 0, we get this one. T equal to 5, we get this one. T equal to 10, and then we plot this one. This is a tedious, simple one. Okay. Sample. For the rabbits in above sample, find the velocity v at time t 15 seconds in unit notation and as a magnitude and as an angle. Now, this is given. But v is vx equals dx dt. Vy is dy dt. So it's very simple to do it. Do the derivative with respect to time t. This is a 2 minus 62, okay? Minus 6. This is a 7.2. This is 0. This is the answer. And Vy equal to dy dt. This is a 0.44t minus 9.01. Right? And then the t is in 15 seconds. We put the t inside. We get the Vx, okay? We get the Vy. Now, Vx minus, Vy is minus, so V is minus 2.1i minus 2.5j. Now look at this one. This is location. The velocity V is, x is minus. This is a positive, it's a minus. Vy is minus. This is positive, this is minus. So this is the V. Well, we know that's tangent to the curve, right? Yeah, this is one. And the magnitude is Vx squared plus Vy squared, square root. Minus 2.1 square plus minus 2.5 square, square root. Get 3.3 meters per second. And the angle, you know that the angle is always y is y, this is angle y over x, it's tangent. Okay, yeah. It's always y over x. This is Vy over Vx. You get a positive number, okay? The positive number. So this angle is minus 130. Sample. For the rabbits in the above sample, find the acceleration A at time t 15 seconds in unit notation and as a magnitude and an angle. This is given. So we get a v. V is dx. Vx equals dx dt. Okay. Vy is dy dt. And ax is dvx dt. Okay. So ax is dvx dt. This one minus 6.0 is 0. And ay is dvy dt. Okay. This one is 0.44. So you see the A is AXI minus 6I plus AYJ, 0.55J. In this case, A is nothing to do with time t anymore. So it is constant. It's a constant acceleration movement. Okay. So t in 15 is constant anytime. Okay. Now we look at this one. A is minus AX. AY is positive, so this is the direction of A. This is the direction of A. The magnitude is AX squared plus AY squared, square root. 0.76 meter per second per second. And theta is always Y over X. Okay, you have two choices. Based on this situation, okay, it is 145. Sample. A particle with velocity v0 equals minus 2.0 I plus 4.0 J in meter per second at t equal to 0 undergoes a constant acceleration A of magnitude A equals 3.0 meter per second at an angle theta 130 degrees from the positive direction of the x-axis. Now, the acceleration is a constant, okay, with magnitude and angle, okay, and the v0 at the beginning velocity, this one. What is the particle's velocity v at t equals 5.0 second in unit vector notation and as a magnitude and as an angle? Now, this is a constant acceleration. So we use the v equal to v0 plus at. Two-dimensional. You have two components. Okay, vx equal to v0x plus axt. Y component, vy equal to v0y plus ayt. Now, we have this one. vx0 is minus 2.0. vy0 is 0.40. T given, we want to find AX and AY. We know A equal to, this is an angle. So AX equal to A cosine theta. AY equal to A sine theta. This is a theta. Okay? So this is a very simple question. Okay? We put it. Okay? AX, AY, can find AX as A cosine theta. 3.0 times cosine 130. So minus 1.93 meter per second. AX is A sine theta equal to plus 2.30 meter per second. V0 given minus 2. So we put this one by one. Vx equal to Vx0 minus 2.0 minus 0.0. AX minus 9.4. T is 5.0. We get Vx. Similar, Vy equal to Vyo 4.0 plus A sine theta plus 2.30 time. You get this one. So we get a V. We take the two significant digital. So this is a run up minus 12. This is run up 16. So this is minus 12I plus 16J now, of course, meter per second, right? Yeah. The magnitude V equal to Vx squared plus Vy squared, square root, okay, is 19.4 meter per second, okay? It's 19 meter per second. and the angle is always tangent theta equal to Vy over Vx. Okay, Vy is 16 or 15.1. Okay, the Vx is minus, so this is minus, we get 127. Take two significant digital, we run up 130. Projectile motion. Assumption. 1. Two-dimensional motion, not three-dimensional in our discussion. 2. Air has no effect on the motion of the projection. It's not true, but ideal situation, we think air has no effect on the motion of the projectile. During its two-dimensional motion, the projectile position vector r and velocity vector r changes continuously, but its acceleration vector g is constant and always directed vertically downward.
How is the vertical motion of a falling ball affected by its horizontal motion? We'll use this device to find out. If a ball is loaded onto the back and the trigger is pulled, the ball falls straight down. If another ball is loaded on the front and the trigger is pulled, the ball both flies horizontally and falls vertically. But how do the vertical accelerations of these two falling balls compare? If we drop one ball vertically at the same time we fire the other horizontally, which will strike the ground first? They both strike at the same time. The vertical acceleration of a falling ball is unaffected by its horizontal motion.
The horizontal motion and the vertical motion are independent of each other. That is, neither motion affects the other. We look at this one. Okay. They falling on the ground, they touch the ground at the same time. That means the vertical motion are not affected by the horizontal motion. This one is no horizontal velocity. This one is with some horizontal velocity. But they are connected with each other through time t. We look at this projectile motion. We know the velocity, the acceleration g is always up towards 1. And horizontally, you don't have any force. Okay. So the horizontal component of velocity is constant, always constant. And vertically, you have acceleration downward. So this is a free fall acceleration, constant acceleration. So get velocity goes slow, slow, 0, and you turn around, get bigger and big and big. Okay. So each time the velocity is a combine of horizontal and vertical. Horizontal and vertical. Okay. We know the free fall acceleration movement very carefully. So horizontal is uniform motion. Vx equal to original Vx0 is equal to V cosine theta 0. This is projectile angle V theta 0. And vertically is a free fall acceleration with the initial velocity V0y. V0y equal to V0 sine theta 0. Okay. Projectile motion analyzed. Okay. We know horizontally is a constant movement with V0x, V0 cosine theta 0. Always that magnitude. And vertically is initial v0y is v0 sine theta is free fall acceleration. So this is always uniform velocity. Vx minus x0, the displacement in x direction is vt. The v is v0 cosine 0 t. And y is free fall acceleration. So the displacement y minus y0 equal to 0 v0 yt minus, because g is go down and our reference y is up in this case, minus gt squared, and voy is vo sine theta o. That's it. That's the one. Now we like this one, t equal to x minus x0 over v0 cosine theta. You put the t into this one. Okay, plug this into one. So they get y minus y0 equal to v0t. T is x minus x0 over v0 cosine 0. And you see, this one, you have sine theta 0, v0. And this one, you have v0 cosine. So v0 cancel out. Sine theta over cosine theta become tangent theta x minus 6, okay? And you have half gt squared, that t equal to x minus x0 v0 cosine c. This is the one, projectile, okay? Now, we usually take x equal to 0 and y equal to 0 as orange of the reference frame, okay? When we take this one 0, we get y equal to tangent theta x minus half g, okay, this is x squared, v0 squared cosine theta squared. The function is, y is a function of x as a x squared. So we know this is a parabola, okay, that's projectile motion, okay. Now, we introduce range. Range is you projectile and you, at the same level, it reaches this distance called the range, usually from horizontal sea level to sea level, or from ground to ground, right? Yeah. What of physics? For the physics is y minus y0 is 0. In this case, you get r. From here, we get time t. Y minus y0, we get time t, okay? We put in t into this one, you get the range. So this one, you make it to 0, you get a t. You put it in here, it is 2 sine theta 0 cosine theta 0 is sine 2 theta 0. v0, v0, v0 squared. So the range is v0 squared over g sine 2 theta. This is a range. So range r is a function of theta 0. And we can tell when theta equal to 45 degrees, sin v0 equal to maximum range. The horizontal range r is maximum for launch of angle of 45 degrees. Of course, with the same velocity v0.
This brass tube points directly at a plastic bottle hanging from an electromagnet. If we put a wooden dowel in the tube and blow into the tube, the dowel is fired straight at the hanging bottle. But as the dowel flies out of the tube, it knocks off a piece of aluminum foil carrying current to the electromagnet. The electromagnet shuts off, and the bottle begins to fall just as the dowel flies out of the tube. Even though the bottle is no longer in the spot at which the dowel was aimed, the dowel still strikes the bottle. Here is a repeat with the dowel fired at a lower speed. These dots will track the positions of the dowel and the bottle at 1/10 second intervals as the last sequence is repeated.
In this demonstration, A small car will roll down a track at constant speed. When the car reaches this point, it will fire a ball straight up as it continues to move. After the ball is fired, will it come down ahead of, on top of, or behind the car? It comes down onto the car. This shot in stop motion shows that the ball stays directly above the car at all times. What will the shape of the ball's path be through the air? The ball flies in a parabola. The combination of constant horizontal velocity and constant vertical acceleration produces a parabolic path.
At what angle should a ball be launched in order to fly the greatest distance before striking the ground? This spring-loaded gun can launch small wooden balls at different angles with the same speed. As we shoot each ball, we will track its position with a line on the screen, using a different color for each angle of firing.
The effect of the air. We have assumed that the air through which the projectile moves has no effect on its motion, a reasonable assumption at low speeds. However, for greater speed, the disagreement between our calculation and the actual motion of the projectile can be large because the air resists or opposes the motion. We look at this, we have a V0 projectile subject with an angle, initial angle 60 degrees. From our calculation, this speed is 44.7 meters per second. You should have range 177 meters. But in that environment of this air resistance, actually it only reached 98 meters. By theory, it should get height 76.8 meters. Actually, it has only reached 53 meters. By calculation, it should last 7.9 seconds in the air, but actually, after 6.6 seconds, it touched the ground. No problem in physics can be solved exactly. It is always necessary to make approximation in solving problems. The trick is to divide the problem into two parts. Simple parts to find the exactly solution. Small part to do your best, or small enough to be neglected. Sample. In the figure, a rescue plane flies at 198 kilometers per hour at a constant elevation of 500 meters towards a point. Direct over a boating accident victim struggling in the water. This is the point. The pilot wants to release a rescue capsule so that it hits the water very close to the victim. After the rescue capsule leaves the plane, it is projectile. Projectile. Now look at question 8. What should be the angle phi of the pilot's line of sight to the victim? And this pilot's line phi when release is made. So the the capsule rescue a capsule will reach around this area. Question B. As the capsule reaches the water, what is its velocity? V in unit vector notation and as a vectitude and as an angle. Now, in order to find phi, we know this is a constant, 500 meters. If we can find the range, not the exact range, okay, that the horizontal displacement, and then tangent phi equal to this over h, we can get a phi. And this is one equal to time, this distance, the time multiplied by the velocity, 50.5 meters per second, okay? How much time it hit one, we can from the vertical, let's see. That's a strategy, okay? Y minus y0, y is here, y0 here is minus 500, equal to v0t minus t. From here, we can find the t, because this is minus 500. Y is going up, so this is 0, this is minus 500. This is minus 100, this is 0. Okay. From here, V0, we know 55.0 meters per second. Theta 0 is 0 because horizontal. So in this case, I can find the t. Okay. T equal to about 10 to the 0.1 second. Once you have a t, we know velocity, this is equal to x equal to V0 cosine 0, this is 0, t. So this is, we get this one, 556 meters. Okay, we take this a reference O, this is x0 is 0. So the x equal to 555.5. And then the tangent phi equal to 555 over 500 equal to, so we get a phi, 48 degrees. Question B. What the speed when he read the water? The speed has two components. Horizontal, this is 55.0 always. Vertical, let me calculate. Okay, we get a t. It started from 0, so this is one is very simple. This is V0 sin theta minus gt. This is a 0. Okay, g 9.8, 10 is t is 10.1, so we get minus 99.0. This is downward. This is horizontal. So v equal to vx I minus vj, vyj. The magnitude equal to vx squared plus vy squared square root. We put this number inside, okay, with x113. And this phi is tangent vy over vx, always y to x. We get theta, okay. This angle is minus 61. So you see, vy is negative number, go this way. Vx is positive, so this is the direction of v, okay? This is minus 61. Uniform circular motion. A particle is a uniform circular motion if it travels around a circle or circular arcs at constant speed. And that is what's happening in uniform circular motion. Look at this one. Okay, it's looking around. Okay, the velocity direction of the particle in the uniform circular motion changes all the time, but it must along the tangent to the circle or circular arc. Although the speed does not vary, the particle is accelerating. That fact may be surprising because we usually think of acceleration as an increase or decrease in speed. But actually v is a vector, not a scalar. Okay. If v changes even only in direction, there is an acceleration. And that is what's happening in uniform circular motion. You see, the velocity change its direction, and it does have a acceleration called centripetal acceleration toward the center of the circle. Now, let's prove it. First, let's see the situation. This is the point. This is a vector v along the tangent perpendicular to r. It's a location. This is x-axis, y. So its position is xp, yp. This is r. This theta, and this is theta. Why did that? This line perpendicular this line. This line perpendicular this line. So they are the same. Okay? Now let's see Vx. Vx here is minus v sine theta. Right? Direction is minus. And what is sine theta? Look at this triangle. Sine theta equal to yp over r. Next, Vy. Vy is v cosine theta. And cosine theta in this triangle, this is xp over r. Okay, this is v. Now, let's see. Let's look at A. A is dv dt. So Ax is dvx dt. We put this one here is minus vyp was inside. And we will see that this v, velocity, speed is constant. R is constant. So we take this out. The leftover is dyp dt. What is this? This is vy, vxy, right? And then vxy. Okay. What is vxy? Further, vxy you could v cosine theta. So put the v cosine theta, we get a v square over r cosine theta minus. Next, we see the ay. Ay equal to dvy dt. dvy equal to this one, vxp over r. And as v is constant, r is constant, we take it out. Inside becomes dxp dt. This is a vx definition. And vx equal to minus v sine theta. Okay? We put the d minus v sine theta, get a minus v square of r sine theta. Now, we have ax minus v square over r cosine theta, ay minus v square over r sine theta. We put this one, we can find the a. A is ax, a square equal to ax squared plus ay squared. We put this one inside. This blue one is ax, okay? And the red one is ay. We take the v square over r square out. We get a cosine square theta plus sine theta square. That's equal to 1, whatever theta is. So we get a equal to v square over r. This is the magnitude acceleration. This is centripetal acceleration we are familiar with in one-dimensional, right? Yeah. Now I prove it. How about direction? Our direction could, this is phi. Tangent phi could ay over ax. This is ay. This is ax. So we cancel out v square over r. We get sine theta over cosine theta is tangent theta. What does it mean? Tangent phi equal to tangent theta. Tangent theta below is just from center to this theta. So what this mean? This means this A is toward the center of the circle. It's directed along the radius and toward the circle center, the centripetal. Okay? Example. Top Gun pilots have long worried about taking the turn too tightly. As a pilot's body undergoes centripetal acceleration with the head towards the center of the curvature, the blood pressure in the brain decreases, leading to loss of brain function. There are several warning signs to signal a pilot to ease up. When the centripetal acceleration is 2g or 3g, the pilot feels heavy. At about 4g, the pilot's vision switches to black and white and narrowing down to tunnel vision. If the acceleration is sustained or increased, vision ceases, and soon after, the pilot is unconscious, a condition known as G-lock for G-induced loss of consciousness. What is the centripetal acceleration in G units of a pilot flying an F-35 at speed V 2500 km per hour, that is 694 meters per second, through a circular arc with radius of curvature R 5.80 kilometer. Pretty dark. Then we put this formula, A equal to V squared over R. We know V, we should 9 to 4. And we know R, we should 5,800. We get 33.0 meter, about 8.5 G. It's pretty dangerous to G-lock. Relative motion. Relative motion in one dimension. A reference frame is a physical object to which you attach your coordinate system. We consider only frames that move at constant velocity. Such frames are called inertial reference frames. The Newton's laws can be applied only in inertial reference frames. Like this one. The location, we have a frame B and frame A. The position P in frame A, we call the PA. This is a PA. Okay? They're equal to PB. This is a PB plus PA. Okay? That is a PA is a PB plus PA. What we do in this relative motion, now I'll show you. We have a PA, we split the P. Put P in the front and A at the back. And in the middle, we put B. We can put any frames. Okay, that's the way I remember relative motion in one dimension. Okay, B can be any letter. This is so crucial. B can be any letter. We take a B out, we put a D. Okay, it's fine. So we put back B. All right. Yeah. We know this one. The position P in frame A equal to the position P in frame B plus the orange of frame B in frame A. Let's do the derivative with respect to time t. What is this? That's a speed. That's speed VPA. But VPA means the speed of P in frame A equal to the speed of P in frame B plus the speed frame B in A. And then we do the derivative on both sides again. And we get what? We get the acceleration PA. The acceleration of P in frame A equal to acceleration P in B plus acceleration B in frame A. And we know that for this inertial frame, they don't have relative acceleration. They only have relative speed difference. So ABA or AAB is 0. So we have APA equal to APB. What does this mean? This means the acceleration of P at frame A is equal to acceleration of P in frame B. We will have a sample to prove it. Okay. Observers on different inertial frames of the reference, their velocity of separation is constant. When measure the same acceleration for a moving particle, acceleration image the same. And for two frames, we have VAB equal to minus VBA. What does mean? You stand in frame A, look at the B, it has velocity. It opposite. You stand in B, look at A. Okay.
We'll use this pair of toy bulldozers, which run at constant speed, to demonstrate how velocities add and subtract. This bulldozer is running on a stationary tabletop. A second bulldozer, which runs at the same velocity, is placed next to the first, but on top of a paper sheet, which can also be moved at a constant velocity. If we move the sheet along the table in the same direction as the bulldozers, how will the velocity of the second bulldozer compare with the bulldozer on the table? When the sheet moves in the same direction as the bulldozer moves, the velocity of the sheet is added to that of the bulldozer, so it runs faster than the one on the table. If we move the sheet in the opposite direction as the bulldozer, its velocity relative to the table is decreased.
Simple. For the situation of the figure and this section, Barbara's velocity relative to Alex is a constant VBA, 52 kilometer per hour. Now this is in frame A, velocity of a B. Okay. And car P is moving in the negative direction of the x-axis. Okay. In this one, P is moving x-axis. Okay. Question A. If Alex measure a constant velocity VPA of minus 78 kilometer per hour for car P, this one looks minus direction. What velocity VPB will Barbara measure? VPB is the velocity of point car P in frame B. Now, we do this one. We've split PA into two. PA, we put the B inside. Okay? And we know that's VAB equal to minus VBA. What we want to find? Now, we want to find VBA. We give VPA and VBA. Okay? VPA is minus 78, is given. VBA equals to 52, is given. Okay? So we put them together, we get the velocity of car in frame B. Barbara look at it. It's minus 130 kilometers per hour. This is velocity in frame B. Barbara looks at it. Okay? Question B. If car P brakes to a stop relative to Alex, that is, happen in frame A, and thus the ground, in time t 10 seconds, at constant acceleration, what is its acceleration APA relative to the Alex? This is the acceleration of car P in frame A. That's very easy. We start definition. A equal to V minus V0 over T. In this case, it's stop. This is 0. Originally, it's minus 78. 10 times it is C. So this acceleration, we get it. And notice that this is not a standard unit. You have to convert it to meter per second. Okay, we have a conversion factor. Okay, so finally we get this 2.2 meter per second. This is for Alex. Now, question C. What is the acceleration APB of car B relative to Barbara during the braking? Okay. Now, we get the same reason. V minus V0T. V, you look at in frame A is 0, stop, but from B is not B, because Barbara itself have a relative speed with the Alex. So this one, D equal to minus 52. And the speed, as we calculate, is minus 130. Divided by time, we get A equal to 2.2 meter per second. That means you measure the acceleration in different inertia frame, you get the same answer. relative motion in 2 dimensions. This is one frame B, this is one frame A, the 2-dimensional. So the PA is what? Equal to PB plus RBA. Now we do the same thing. We split P and A, put P in front, A back, put in B between. Okay, this is how I remember this relative motion formulas. Okay. And we do the derivative with respect to time t on both sides. We get V. VPA equal to VPB plus VBA. And we do the derivative again, we get APA equal to APB, because ABA is 0, because they are inertial frame. They don't have relative acceleration. So we get this one. Also, we have VBA equal to minus VAB, and ABA is 0.
We'll use this ping-pong ball on a string and a glass tube to demonstrate the vector addition of 2 velocities. The ball is first pulled straight up the tube, giving it a velocity in the vertical direction. Now the tube is moved to the left with the ball at the bottom, giving the ball a velocity to the left. When the top of the string is held stationary, while the tube is moved to the left, the ball moves up the tube and to the side at the same time. The vertical and horizontal velocities of the ball have equal magnitudes, and their sum is a velocity at 45 degrees to both.
This toy bulldozer, which runs at a constant speed, will be used to show how velocities add together in 2 dimensions. The bulldozer is set on a paper sheet that can be pulled along the table at a constant velocity. The bulldozer is first set up to run directly across the sheet, and it follows this path. This time, the sheet will be pulled to the right at half the speed of the bulldozer. What will the path of the bulldozer be? The bulldozer moves at approximately 27 degrees to its previous path. What will the path be if the sheet is pulled at the same speed as the bulldozer? The bulldozer moves across at 45 degrees to its original path. If we now aim the bulldozer at 45 degrees to the left, how fast must the sheet be pulled to the right if we want the bulldozer to move straight across? Pulling the sheet to the right at approximately 7/10 of the bulldozer's speed makes the bulldozer move straight across.
Simple. In Figure A, a plane moves due east, direct toward the east, while the pilot points the plane somewhat south of east, because you have a wind, towards a standing wind that blows to the northeast. Okay. So this one plus this one equal to this one is called east. The plane has velocity VPW relative to the wind, V of plane relative to wind, with an airspeed of 215 kilometers per hour. This direction, I know this one, VPW. Okay. Direct at angle theta southeast, this direction. Okay, I don't know theta. The wind has velocity V wind ground relative to the ground with a speed 65.0 kilometers per hour. This is the one, 20 degrees. directed 20.0 degree east of north. East of north. Question: what is the magnitude of the velocity VPG, the velocity of plane relative to the ground? This is how much. We know direction, we don't know the magnitude. Okay. And what is theta? We want to find out two things. Let's see, set the frame is XY. Okay. Let's see the moving part, the sign. The plane is called P. Okay. The reference frame, okay, you have the ground, you got a G. The wind, you got a W. Okay. So this is a VPW, means the velocity of plane with respect to time, wind. Okay. Okay. This is VWG, means the velocity of the wind relative to ground. And this is what we want to find at the velocity P, plane, relative to ground. Now we same thing. We split the PG into two. Put the wind inside, because basically out of situation. So what is happening is that the velocity of plane in the ground equal to the velocity of plane in the wind plus the velocity of the wind plus relative to ground. Okay. This is the vector equation. It has two components. Okay. First, we allow the y direction. Why y direction? Because this is along x, z, v. This is 0. Then we put this side. Plane in ground along y direction is 0. Okay, because it goes this direction. And the plane to the wind, you see, is this one. Okay, this is the big one. This one, this is a sine theta. Sine theta, this one, this one. VPG, so I said this one. This is V is minus sine. And for this ground V, this is a positive y direction, cosine 20 degree. Okay. In this one, we put this one, we put this one, we can find the sine theta, we can find the theta. Okay. We get a theta equal to 16.5 degree. Then x is y, x direction. This is what we want to find. Okay. Equal to VPW x plus VWGX. That's VPWX equal to VPW cosine theta. Theta is 16.5. That's VWX, VWG sine 20 degree. Okay, so we can find this one because we know both of them. Next lecture, chapter 4, force and motion. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.